हेलो। हेलो। समीर, आवाज जा रही है? समीर। हेलो। समीर, आवाज आ रही है कि नहीं? रिस्पॉन्स नहीं कर रहे हो? Okay, so let's start to the class. In the previous class, we are explained the connection of this DC shunt motor. So just we try to write their speed torque characteristic. The speed torque characteristic of the DC shunt motor. In the previous diagram, we already shown there the connection diagram of the DC shunt motor, how we can connect. So just we apply here the voltage KVL equation in the DC shunt motor, and just try to find out their speed torque characteristic. So we can, if we apply the KVL equation in the DC shunt motor, we can just write here V equal to EV plus IARA, where V is your input voltage and EV is your back EMF induced in the motor, and IA is your armature current of the motor, and R is your total resistance of the armature circuit, that is rheostat plus armature resistance RA. Okay, so these are the specification of the parameters for the DC shunt motor. As we know that the EMF induced or back EMF induced in the shunt motor is denoted by EB equal to K phi omega, where K is your constant term of the machine and phi is your flux, average flux per pole, and omega is your angular velocity in radian per second. Okay, where K equal to nothing but Zp by 2 pi a, where Z is your total number of conductors in the armature circuit, and N is your number of parallel path in the armature circuit. Okay, and sorry, N is your, yeah, and P is your number of pole in the machine. This one is your A here. Actually, A is your number of parallel path. This one is A, not N. So number of parallel path in the armature circuit, and phi is your flux per pole, and omega is your angular velocity in the radian. And what we can represent the torque equation in the DC machine. It means T equal to constant K phi into IA. Okay. So torque equation in the DC machine is equal to K phi IA, where K and phi are similar to this one, whatever we explained here. That means constant term K equal to Zp by 2 pi A, and phi equal to again flux per pole, and IA is your armature current. Okay, so if these two value, that means EB back EMF and torque is put in this equation, that means here. Okay, so torque equal to K A K phi IA. So IA equal to how much? We can represent here from this IA is equal to nothing but so we can write here, that means omega equal to Vt minus IA RA by K phi. Okay, since put this value EV equal to K phi omega. So if you find the terms of omega, that means angular velocity equal to V minus IAR divided by K phi. Is not. And as we know that the torque equation is equal to T equal to K phi Ia. So just to find here Ia value in terms of torque and put here the value of Ia in this equation. Okay. Omega equal to V minus IAR divided by K phi. If you find the Ia value in terms of K phi, so we can write here Ia equal to nothing but T by K phi. So just put in this equation the value of Ia and just simplify. Okay, so if we simplify this equation, then we can obtain the value of speed in terms of torque. Okay, that is nothing but V by K phi minus, put here the value of Ia equal to T by K phi, that means T by K phi into K phi already in denominator. So denominator part will becomes K phi whole square and numerator part is nothing but TR. Okay, so this term V by K phi, since the flux is constant and the supply voltage or input voltage of the motor is also constant, so this term may be represented as K phi, K phi, uh, K phi equal to constant. So if in DC shunt machine flux is almost constant, so this new term of constant can be involved here, that is nothing represented by nothing but C equal to K phi. So we can simplify this equation, that means omega equal to V by C minus TR by C square. Okay, that means a speed dependent on the input voltage and torque and armature resistance. Okay, this denominator part is your constant. So if you change the input voltage, so your speed will vary. If you change the torque, that means armature current, which is T by K phi, and depends on the armature resistance as well as the rheostat. So if you change these three parameters, that means input voltage, torque, and resistance, total resistance of the armature circuit. So armature circuit resistance RA, that is your fixed, but rheostat, whatever you connected in the armature circuit, that you may vary. Okay, so if you vary armature resistance or rheostatic resistance is fixed. Rheostatic resistance, we can say that the rheostatic or external resistance connected in the armature circuit and torque as well as the input voltage, then your speed will be vary. Okay. So how you can the characteristic of, we can draw the characteristic that we nothing but here. So there characteristic of the speed versus torque. So this is your constant speed that is represented by omega 0, almost constant, and the armature resistance drop, that means linearly. So drop slightly, that means from the no load speed. This is your dotted line represent the no load speed of the motor. Okay. If R1 equal to, consider that means RA armature resistance, that means slightly actual natural characteristic will becomes slightly slower than the actual no load speed. Okay, so this one represents the natural characteristic, that means slightly drop from the no load speed. Okay, and again if you represent some another resistance on the some another resistance, that means R2. Okay, so we just also get the variation of speed and torque with the help of variation in the resistance R, that means external resistance plus armature resistance. So armature resistance is your almost fixed. So you have to change their external resistance, or we can say that the rheostatic resistance value. Okay. So if R1 is more less than R2 and R2, so R2 is your higher resistance, that means slightly drop more compared to the R1. And if R3 is more than R2, then this characteristic is again drop compared to the R2. Okay, And these things, we can say that the R1 is more than R1 is less than R2, R2 is less than R3, and R3 less than R4. So when you increase the resistance, your external characteristic of the speed versus torque characteristic will be changes of the motor. Okay. So natural and rheostatic, that means natural, we can say that the rheostatic resistance you have to consider 0 for R1, and if you add some external resistance in the armature circuit, that is your R2. Some another resistance add, that will be represented by R3, and if another resistance add in the armature circuit, that will be represented by R4. Okay. So R1 is less than R2 and R3 is less than R4 and R4 is less than R5. So this is the speed torque characteristic of the DC shunt motor. You have to keep in mind. And next we can just drive there. How we can construct, that means yeah. So this one, how we can construct construction of the speed torque characteristic. So just we put here, that means K phi omega L equal to V minus IL load current into RA. In place of armature, just we put here IL current. Okay. So IL is your nothing but full load armature current, and omega is your full load speed of the motor. Okay. So we can write here for the value of omega L equal to V minus ILRA, nothing but ILRA, and omega 0 equal to represent the no load speed of the DC shunt motor. No load speed of the DC shunt motor, that means you have to put the load current is 0, then hello. So here IL equal to full load armature current and omega L is your full load speed of the motor. So just find here the no load speed, that is omega 0, that is nothing but V by K phi, and this is your, if you take common, omega L equal to this one, if you take common, that means 1 minus IL RA divided by V. Okay. So this is the relation of full load speed versus no load speed. Okay. So their characteristic we already seen in the previous diagram. Okay. If resistance, external resistance changes, then your characteristic is slightly drop below the previous rheostatic resistance. So the armature resistance RA, which is not given in the machine, so we can find out by the approximate, by assuming the half of the losses of the motor. The armature resistance not mentioned in the nameplate of the motor, then we can just consider the half of the losses of the motor at the rated torque, copper loss. That means the assuming the maximum efficiency occur at the rated load. Okay, so maximum resistance occur at the rated load, that means is equal to nothing but the half of the ohmic loss. Okay, so IL square RA ohmic loss equal to 0.5, 1 minus efficiency at full load into V into IL. Okay, so just we can find from this equation the value of armature resistance RA. If your efficiency is given of the motor and input voltage and load current, then we can find out armature resistance of that particular machine. Okay, so armature resistance equal to 0.5 into 1 minus efficiency into V by IL. Okay, V by IL. So And load torque equal to just you can put here the value of torque equation, that is nothing but K phi IL. So phi is your constant in the distance motor. So we can this phi and K put by the another constant. So total is your constant. So just put your constant another constant C. That means load torque is directly proportional to here load current. Okay. So omega RH, that means the rheostatic load resistance, is just put here the value of IL, that is nothing but TL by C. Okay, so if you simplify these two equations, you will get the value of omega RH equal to 1 minus IL into RA plus RH. So you already find here the value of RA. Okay, so just put here RA, and if you change the rheostatic resistance value, then your rheostatic load as a velocity will also change it. You can find out the relation between these two. Okay, so short circuit torque, that is nothing but the I short circuit by I full load current into load torque. Okay, that is TL. So V short circuit, I short circuit equal to V by R, and so omega equal to omega naught, that means no load speed into 1 minus T by short circuit. Okay. So this is the relation of a speed and torque for the, that means no load speed into 1 minus T by T short circuit. Okay, so if you consider one example, moreover on this DC shunt motor. Okay, so a 220 volt, 21 ampere, 1000 rpm DC shunt motor has armature resistance of 0.05 and field resistance are given on the 220 ohm, and field current at the various EMF induced value are given. That means you maybe know that the EMF induced and field current, that means flux, is directly proportional to the EMF induced is directly proportional to the flux. So that means field current. So if field current is changes, that means EMF induced is changes. Okay, so given here the parameters of field current, various field current value corresponding to that EMF induced value is given. So calculate the speed and the torque developed by the motor with the help of load current under each of the following condition. That means no external resistance is included. तो हम लोग इसका स्पीड कैसे फाइंड आउट कर सकते हैं? Just in this problem given to you, whatever data you have to just note down. That means input voltage given to you 220 volt, 21 ampere, and velocity is given to you in radian per second, revolution per minute, 1000 revolution per minute. DC shunt motor has armature resistance, that means RA given to you 0.05. Okay, and field current 220 ohm. The magnetization curve for the machine is given in the following table. Magnetization curve is nothing but the EMF field current versus EMF induced. That means EMF induced is directly proportional to the field current. So we have to just calculate here the speed and torque developed by the motor with the full load under each of the following condition. That means no external resistance included. A resistance of Etna is connected in series with the armature, and a resistance of 110 ohm is connected in series with the field winding. तो यहाँ पे just हम लोग input voltage we note down here the 220 volt, and RF, that means field winding resistance is represented by RF, that is equal to 220 ohm, and I line current, input current is given to you total, or line current, you maybe say that 21 ampere, and armature resistance, that is 0.05, and velocity in revolution per minute, that is 1000. Okay, so input current is nothing but the summation of field current plus armature current. That means If plus Ia equal to given to you 21 ampere. You know, I1 plus Ia given to you 21 ampere. So how we can find out the value of Ia? We already given in the problem I input current. So first of all, we have to find out require to find out the field current. So field current, how we can find out field current? That is nothing but input voltage divided by field resistance. Okay, so input voltage is your 220 ohm and RF is your 220 ohm. So what is the value of IF? That means field current. 20 by 20, 220 by 220, that means 1. So IF equal to 1. Now we can find out the value of armature current. That means IA equal to I input minus IF. Nothing but that means 21 minus 1. That means IA equal to armature current equal to 20 ampere. Okay, so you can easily find out IA. That means armature current. Okay, so this is the how we can find out the armature current. That means 1 ampere, and IL. That means armature current, IA may be represented by IA. This is your line current. That means 20 ampere. So, as velocity in given revolution per minute, we want to just convert in radian per second. Okay, so 2 pi n divided by 60, the relation of angular velocity and revolution per minute. So, if you want to convert the revolution per minute, then you have to just multiply with 2 pi by 60. Okay, so put here the value of n, that means revolution per minute, and convert it into the radian per second. Okay, so 2 pi into 1000 by 60. If you simplify this equation, you will get the almost 200. 2 pi into 1000 by 60, so almost equal to get 104.72 radian per second. Okay, now you know that the C is your constant, that means K phi. So K phi equal to constant value, you have to just require to find out, that means V minus IA RA by omega. So V equal to 220 ohm and IA equal to 20 into RA given to you 0.05, and omega you already find out here. That means 104.72 radian per second. So if you convert this equation, simplify, then you will get the C value, well, that means constant value in equal to 2.09. Okay, volt second per radian or Newton meter per ampere. The graph is linear, so only 2 points are needed. That means no load speed omega 0. We require to no load speed omega 0. That means speed, we have to calculate the speed. Since in the first case we have given that no external resistance. Okay, that's why we consider here our rheostatic value is 0. No external resistance is included in first case. That means Ra rheostatic equal to 0. So simply here put the Ra. Okay, actually this resistance is Ra plus R rheostatic. So rheostatic value is given 0. So only put the Ra value, that is nothing but 0.05. Okay. And no load speed calculated, that is nothing but 105.26 radian per second. Now this angular speed converted into the radian per revolution per minute, then just multiply with the reverse of that one. That means 60 omega 0 divided by 2 pi. is not. So 60 omega 0 by 2 pi, that means 60 into, put here the value of omega 0, that means 105.26 by 2 pi. If you simplify, then you will get here the value of pi equal to 3.14, and simplify this equation. After that, you will get the 1005 rpm. Okay, 1005 rpm. So omega L, whatever the relation we have derived here, that means no load speed in the this relation. So you may be put here omega L of this equation. That means, yeah, put here in this equation omega L equal to 1 minus IL RA by V into omega 0. You already find out the value of omega 0. So now the put of IL, that means the full load current, into RA by V. Okay, and just find out the full load speed. So just put on this equation whatever the parameters you find out. Already find out. Okay. So just put here. That means omega L equal to 1 minus IL, that is nothing but 20 into RA by V into omega 0. So omega 0 equal to 1500 RPM. Okay. So just put here the value of omega 0 equal to 105.26, and okay. So just put here the value of omega 0 equal to 105.26, and armature current equal to 20 ampere, and armature resistance is 0.05. Okay. And if you simplify, then it will be converted in radian per second, that is 104.78. And again, if you want to convert in revolution per minute, that means full load is equal to 60 into omega L by 2 pi. Okay. So put the value of omega L, that means you have to obtain the 104.78 radian per second. And if you simplify, then you will get the almost 1000 RPM. Okay. So full load torque is your 1000 RPM. And torque is equal to nothing but C into IL. So C already you have find out. You already find. So put the value of constant, that means C, that is nothing but 2.02. You already find. Okay. And put the I armature current equal to 20. So torque is your 41.8 Newton per meter. And for the second case, in part B, you have to consider your static resistance value, that is given as how much? 0.05 ohm connected in series with the armature resistance. Okay, so total resistance will becomes R equal to RA plus rheostatic resistance. What is the rheostatic value here given to you? 0.05. Okay. And just now put here for the part B, means you will get the value of, again on the same formula, that means omega RH at full load into 1 minus armature current into total resistance. Here the total resistance, that means 0.05 plus 0.05, but in part A only 0.05. Okay, armature resistance. So this value will becomes how much? 0.1, and V is already given to you 220. So just put on 1 minus 20 into 0.1 divided by 220 into omega 0. So omega 0 is how much? That means 105.26, is not? omega 0 is your 105.26. So if you simplify, then that means 1 minus 20 into 0.1 divided by 220 into 105.26, that is equal to almost nothing but 104.3 radian per second. And again, if you convert in revolution per minute, that means 60 omega RHL by 2 pi. So put here the omega RHL value, that is nothing but 104.3 radian per second. And again, here the value of pi, you may be put as 3.17. Okay. So 60 into 104.3 divided by 2 pi, that is, if you simplify 2 pi and this equation, then you will get almost equal to 996 RPM. Okay. And full load torque equal to same as the previous one, since the torque is not dependent on the external resistance of the armature, as you maybe see the equation of the torque. Okay, so torque do not depends on the external resistance in the armature circuit. So whatever the torque obtained in the part 1, that is same here, that means 41, you may be see the equation of the torque at the full load, that means C into IL. Okay, so do not depends on the rheostatic resistance connected in the armature circuit. So whatever the torque we obtained in part A, that is same for the part B. Okay, now you just solve for the part C. In part C, what we have to consider, that means external resistance is given as 110 ohm. Okay, so 110 ohm, if your rheostatic resistance connected in series with the armature resistance. So what is the total resistance value in the armature? That means RA plus RH. So RA is given to you 0.05 and RH is given here in part C. That means 110 ohm. Okay, so you just find out their value of, it's in your IF is here. Sorry, 110 ohm resistance is connected in series with the field winding. In part C, you maybe see there a statement of the problem. The resistance of 110 ohm is connected in series with the field winding. What was in part B? That means resistance 0.05 connected in armature. Okay, so you have to concern where the resistance connected, either in armature circuit or in field winding circuit. Okay, so in part B, you have to connect it 0.05 resistance in armature circuit, but in part C, you require to connect 110 ohm in the field winding. So if any resistance connected in field winding, that means obviously we have to change the value of field current. Okay, since the field current, that means IF equal to V by total resistance in the field winding. So field winding resistance is changes here, that means 101 connected with the field winding. So total resistance becomes how much? Field winding resistance is 220 ohm in previous and another 110 ohm connected in field winding. So total resistance how much? 220 plus 110 is not. So total resistance is your 220 plus 110 ohm. That means 330. Okay. So just find the value of field current V by how much? Total resistance in the field winding, that means 220 divided by 220 plus 110 ohm. That means field current is your 0.67 ampere. So now calculate the magnetization curve for this from magnetization curve for the 162 volt back EMF. You maybe get the value of EV, that means constant value. You just find out, that means constant value equal to how much? EV by omega. So 162 volt back EMF, you maybe just since your IF changes here, so back EMF is also changes since the back EMF is equal to K phi omega, is not? So K phi omega, that means you want to find your constant, that means K is already constant, so K phi is replaced by another constant, any constant, that is C. So just to find out the constant term, that means EV by omega. Okay, EV given to you 162 volt and omega equal to, you already find their value 104.72. So constant is change here, that means 1.55. See, not 1.55 volt second per radian or Newton meter per ampere. Okay, so omega 0, that means a no load velocity in radian per second equal to V by C. So V is already given to you. And that means 220 volt divided by whatever you obtain the value of C, just put here, that is nothing but 1.55. If you solve this 220 by 1.55, then you will get almost 142 radian per second. Is it not? So now you again maybe can, if you want to convert in revolution per minute, then convert, just put on the formula whatever for the relation between the radian per second and revolution per minute. That means N0, that is no load velocity in revolution per second revolution per minute, that means 60 into omega 0 by 2 pi. Okay, so 60 into 142 divided by 2 pi, that means 2 into 3.14. If you simplify this, then you will get almost 1355. And you again just find out the value of full load torque value, that is nothing but constant term into load current, that means armature current, whatever you obtain, that means this constant term C. Okay, so just put the value of this in torque equation, that means C into armature current. So 1.55 into armature current, that is nothing but 20. Okay, so if you simplify this equation, then you will get the torque value, that is nothing but 31 Newton meter. Now we want to find out the full load angular velocity in the radian per second. So omega L equal to, again put on this formula, that means in this formula whatever 1 minus ILR by V into omega 0. So put the value of omega 0 equal to 142 and ILR and V. So just put on this equation, that means 1 minus 20 into, what is the value of armature current? Armature current 0.05, is it not? No any external resistance connected in the armature circuit. So whatever the armature resistance given in your problem, that is remains here, that means 0.05. Okay. External resistance put here in part C in field winding. So do armature resistance do not change, whatever the armature resistance given in the problem, that means 0.05. Okay, not. So 1 minus 20 into 0.05 by 20 into omega 0, that means 142. Okay, So if you simplify the equation, then you will get the full load angular velocity in the radian per second. That is equal to nothing but if you simplify this equation. Okay. If you simplify this equation, then you will get almost 141. That means 1 minus 20 into 0.05 into divided by 220 into 142. So if you simplify this equation, numerical value you will get the almost in 141.35 radian per second. If you again want to convert in revolution per minute, that means 60 into omega L divided by 2 pi. So 60 into, put here the value of omega L, that means 141 radian per second divided by 2 into 3.14. So you almost get the value of full load velocity in the revolution per minute, that is equal to nothing but 1300 divided by 50 if you put this value. Okay, 141 into 60 divided by 2 into 3.14. Okay, so we can solve problems like this one. Any numerical problem you can practice. Okay, so right. We stop here, and in the next class we will discuss things.